Good afternoon, everyone. So in the end of last lesson, we were discussing a little bit the problem of first passage time. We have a stochastic process in generality. The stochastic process starts, if you want to think about space, it starts somewhere in space, and then there is some trajectory. The trajectory is, of course, random. And then you ask, when will the particle starting somewhere in space will arrive somewhere else in space for the first time? The examples of this problem are very general, because many things you do for the first time in life, and then you're happy. The first time you meet your girlfriend or boyfriend, things like that, is the first passage time till some event. So, of course, we cannot describe all these first passage times, but we are describing a very large class of first passage times where the random process has no memory. That means that the probability to make a jump along the path from some point to another point is independent of the whole history of the path. These type of processes are called Markovian processes. And they're very, very wide, and the best well-known example is simply Brownian motion. So, for example, we can consider a random walk on a lattice, and I'm plotting here the lattice. So I'm plotting a cubic lattice in space. And you think about a particle, if you want an electron, and it can be either on this location or in that location on the vertices, or on the atoms. And the first passage time problem is the following. Let's say we have some absorbing boundary or absorbing point. Absorbing, what I mean by absorbing is that the process will stop once the particle arrives in that point. And here you have some initial condition. So this is the initial condition. And we are asking how long will it take this particle that started here to arrive here. Of course, for that, we need to define what is the stochastic process and what are the paths of this particle. So only for you to have something specific in mind, let us assume that it's doing a simple random walk on this lattice, which means that with probability in 2 dimensions, with probability 1/4 it goes up, with probability 1/4 it goes to the left or the right, and of course with probability 1/4 it goes down, because this is just in 2 dimensions. And then you have a path. So you are here, you flip a coin. Let's say with probability 1/4 you arrived here, and then after that you're going here, and then by chance you arrived here. So here, after 1, 2, 3, 4 steps, you saw the first passage time. That is the number is 4. Of course, what could happen is something very different. Let's say by randomness, you chose an initial condition that goes like here. Maybe then it will go like there, like there, like there. It will go far away. And you can imagine that there are trajectories that are rather, let's say the distance initially is rather close. This is also an important factor. But let's say they are rather close, then you come back very quickly sometimes. But some other times you go far away, and then it will take you a huge time to come back, because this is a random process. It's a random process which is also not biased. There are many, many scenarios. For example, if I walk in 1 dimension, and this is my lattice now in 1 dimension, and I start here, but let's say I have a force in this direction. Here I have no force, so by force I mean the probability to going up, down, left and right was equal. That is mean that you have only diffusion, you don't have a bias. So with the force, what will happen? You will go in this direction and hope you will reach this point kind of quickly. Intuitively you understand this. Of course, we need to translate this force for probabilities of jumping left and right. So if you have some small probability to jump right, then not always you just go tuck, tuck and reach. You can go also backwards and then like that. On the other hand, if I start here and the force is in this direction, then, the same direction, This is the direction of the bias. So again, what is a bias in random walks? What's a bias? What's an external force, which is constant? And we'll soon need to quantify how you relate the concept of force to biases. But by bias, I simply mean that here I have a probability to go half plus epsilon, and in the other direction I have half minus epsilon. So this, I'm here and I toss a cone, and there's a higher probability to jump to the left and less to the right. And that creates a net average drift in this direction. When epsilon is 0, we call it a non-biased random walk. That means there's no external forces. If epsilon is small, then you have a small chance of still going against the force. But eventually you'll come back and go this way. And of course, if epsilon is half, then each time step you go tack, tack, and then it's deterministic. That means if you had your epsilon equal half, you toss a coin here, then you jump here, then you toss a coin, you are here, and then you coin here, and then what will be the first passage time distribution? It will be a delta function on 3. So going back to this example, depending on which direction is the force, sometimes the particle, you kind of easily understand, it goes to the absorbing boundary. While here, what will happen? You can go the other direction. And then there is a probability that you'll never come back. So the most basic question is, there are two questions in this game. A, will the particle, after many, many, many steps, eventually come back at least one time? That is called the recurrence. Recurrence means that the particle eventually comes back. The answer is yes or no. That's the question. Will it come back or will it not come back eventually? You don't care when it will come back. Now, then you can ask a different question. What is the distributions of the times when it comes back? So let's say it will come back with probability 1. What is the probability density function of these transition times from here to here? And even if there is a probability that it will never arrive, there is a probability only, it doesn't mean that it will never arrive. It means in probability it doesn't arrive. Which means that you also can look at the distribution of the first passage times, but they will not be normalized because some trajectories come back and some trajectories don't come back. So we will, the basic equation for how to calculate these first passage times was given already in previous class, and now we are going to discuss it in more detail. But I just wanted to explain here that there are a vast number of problems that you can solve in first passage times, and this is of course natural from your daily experience. But let us have in mind some examples that you can more or less follow what I'm saying soon. So let us consider, as an example, random walks on lattices. But don't consider this in one dimension only. Don't consider it in 2 dimensions. Think about also 3 dimensions. And if you have imagination, think about 4 and 5 and 6 dimensions. For simplicity, just look at a cubic lattice. So this is a cubic lattice, and you understand what is a cubic lattice in 3 dimensions. Just you add here some dot. It's on a cubic structure. And again, just for simplicity, we can do all kinds of lattices if you want. This is a one-dimensional cubic lattice. The distances are the same. And when I mean a cubic lattice, I mean all transitions to nearest. The transitions are only to nearest neighbors. The transitions are all uniform in all directions the same. So this is a simple random walk with no bias, jumps to nearest neighbors. Now, in one dimension, I'm going to tell you one of the main theorems in this field given by a mathematician called Polya. And what does he say? And this is what we're going to prove. He says the following. If you walk in dimension 1, then the particle always will, you start somewhere, you measure somewhere else, the particle with probability 1 will come back. That is, you measure with probability 1. It might take a short time, it might take a long time. This time depends on the distance between the initial condition and the measurement. But eventually the random walker will come back, and you will measure it. It means the following. Consider you live in one-dimensional. You have a chemical center here and a molecule moving here, and it's doing diffusion, Brownian motion. Eventually, these guys will meet and make a chemical reaction. If you do the same in 2 dimensions, you'll get the same result. The particle in 2 dimensions, no matter where you start, with no biases, and the system is infinite, it will reach the absorbing point. However, if you do it in 3 dimensions, sometimes particle A will reach this origin where you are absorbed, and sometimes it will not. So this is called a non-recurrent random walk. In dimension 3, you don't always recover. Why? Imagine this is in 3 dimensions, so you can go also outside. So sometimes, let's say you start in the nearest neighbors, but sometimes the particle diffuses and then it goes somewhere to infinity, and you never come back. You can easily understand that in dimension infinity, if the dimension is very high, this is obvious. Because what you have here is next to your initial condition, you have many sites. So even if you start next to the very close, from here you see I can go to 4 points. In dimension 3 I could go to 6, in dimension 1 to 2. So as the dimension becomes larger and larger, the number of nearest neighbors is becoming bigger and bigger and bigger. And then the chances of you just finding one different location is diminishing. This fact that you come back in 1 dimension and not in 2 dimension, and in 2 dimension but not in 3, also means something on the filling of space. So if I look at the path of the particle, in 3 dimensions you will leave behind some dots where you don't visit, while in 2 dimensions eventually you fill in slowly all space. And in 1 dimension it's also obvious, because if you reach from here to here, all the points in between will be visited. This is an example of a kind of a qualitative shift of the dynamic of the system when you change dimensionality. And many things in physics depend on the dimensionality. And just to clarify, while we live in dimension 3, it doesn't mean that we don't have objects in dimension 2 or dimension 1. For example, a surface is 2-dimensional. So if you have, let's say you have the cell, and on the cell you have a membrane, and on the membrane you have some protein, and this protein is looking for something. So it's doing diffusion more or less on a 2-dimensional object. Of course, there can be some bumps on the membrane, but this is minor. And then we'll say this is a 2-dimensional random walk. And if you have a kind of a small channel, which is long, and you have a particle here, that's like a 1-dimensional random walk. So it's not that dimension 1 and 2 are not physical. They are very physical in many situations. And you can imagine even situations with dimensions higher than 3 are important. For example, if you are not searching in physical space, but in some more abstract, for example, trees in computer science, they have higher dimensions and things like that. You don't need to limit yourself to real space. Anyways, in all our discussion on the recurrency, it's super important that our system is infinite. So if you have boundary condition, for example, reflecting boundary condition, you want to put your system in a box which has finite lengths, then what will happen for any dimension, any random walker, the system will eventually come back. That means you will go far away, you will hit this boundary, and then you will come back, and then if you wait long enough from any initial condition, you will reach this boundary. Again, some people might naively say, okay, but every system has to be finite. That's absolutely wrong. Of course, the universe is finite, that's true, but the question is about time scales. So let's say you have a finite system. Eventually, the particle can diffuse, hit this wall, come back, and okay. But let's say the distance between here and here is such that it will take the particle 200 years to arrive on this boundary and then come back. So from our point of view, the system is infinite. So it's a matter of time scales, actually. So you have to make common sense. The system might, in practice, be finite, but if you are looking and observing the system in a finite time and it cannot reach the boundaries, then it behaves as if it's an infinite system. You don't care about the boundaries. And then you will see all these phenomena that it doesn't come back or does come back depending on the dimension you are in, etc. This is basic common sense. Okay, so let us now, if there's no questions, let us go and treat this problem. And the main idea, which it was in Schrödinger's work, I think, in physics for the first time. Maybe Polya also thought about this. I actually don't know. The idea of Schrödinger was to relate two problems. One is the first passage time, which is the new problem. And the other one is the diffusion or the random walk on the lattice problem that I assume now you are all expert on. So this is what we studied at the beginning of the course. So the idea is, in pictures, is we have two objects that are interesting. So let us just schematically plot it. So we have, we want to define some initial condition. For example, this is the initial position. And we will denote it by R0. And it's a vector because we are working on a lattice, let's say, in dimension 3 or 2 or whatever. So I think this is an obvious notation. And then you have some point R. And this is the final point. You want to know the guy does a random walk and eventually reaches this point R. And there are two types of and time is discrete. So my time here is discrete. So I have n, and it will be denoted by n. This is time. And you will have 1, 2, 3, etc. Tack, tack, tack. Which means that on each vertex I toss a coin and then it jumps left, right, up, down, and then I update my time by 1. So I'm doing this. This is called discrete time, and I'm also working on discrete space. This is just helpful because it defines the path very precisely. But this will also yield some summations instead of integrations. But OK, that's a technical detail. So on this type of problem, I can first of all ask, what is the probability after time n, after n steps, to be an R starting on R0. So the random variable here is R. So this is just the usual propagator. So if I started here, I can jump up, down, left, right. So after one step, there's probability 1/4 to be on one of the nearest neighbors. And after that, it will propagate to the next nearest neighbors and come back. So this is, of course, we solved this exactly in the previous classes. So we know everything on this, quote unquote. What do we mean everything? We have a formalism for this. I'm not saying that you know immediately how to solve it for all lattices in the world, but you know in principle what to do. Just to remind you, what you need to do is you define the characteristic function of this problem. That is, what is the step, one step here, and then you can calculate with the Fourier transform technique, we can calculate this. But even if you don't know how to calculate, let's say you simply run simulations and you got this thing, or you calculated it for short times, for n not too big at least, it's easy to calculate this by propagating. You got it from somewhere. We don't care at the moment how you find this. This is everything that we know. And this is a probability. It's nothing to do with the first passage time per se. The claim is that if you know this, you can also know the first passage time distribution. So the first passage time distribution is, again, the same problem. So here again, I have an initial condition. And here is my final position. And here I'm going to define the probability to start at R0 and be at R for the first time at time n. So this is a probability. This is a number between 0 and 1. This probability is the following. So I move, and then at time n, I can make a jump here, but it has to be for the first time. So do I arrive here for the first time? This is why we use the word f for the first time. It's very different, of course, from this object, because here I don't care. I could have visited this point a million times before. I just care what is the probability to be on point r at time n. And the number of times I visited this point could be as much as I want. Of course, it will be less than n, but any number is legit. It could be for the first time, it could be for the second time, or the third time, or whatever. And this is what I'm after. Eventually, now I want to know what is the probability of visiting R at least once. That is the sum of all these probabilities, the sum over Fn. Now this number can be either bigger than 1 or smaller than 1. It's some number between 0 and 1. It could be 0, it could be 1, or anything in between. This is the sum over all these Fn's. Then we say if this number is less than 1, sum over n. So what is the probability that in the first step you made the jump? So what is the probability if you start here, this f, to reach this point when n is 1? The answer is 0. Why? Because after one step you can be here, 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 or here. Of course, you could define the random walk differently when you allow long jumps, but that's a different story. So f1 is 0. f2, there is some probability to reach here. f3, there's some probability to reach there for the first time, etc., etc. Okay, is it clear? So the sum of the firsts after n, over all the n's, it can be either less than 1. If you start at the origin, this is called non-recurrent. Or it could be 1, this is called recurrent. That means that eventually you reach the destination, but you don't care when. Of course, I can also calculate averages. For example, what is the average time till you, if this is a sum, this is easy to understand, but I can calculate what is the average time till the first passage is simply nfn. This is if you are recurrent. Why? Because only then you are normalized. The sum of the fn's are normalized. They don't have to be normalized because maybe you don't come back. So when you will come back, then we can define the average first passage time. Our focus will be on this quantity and not on this quantity. We will, in the next lesson, we will study a little bit this quantity, but with a totally different method in continuous time, not in discrete time. And it turns out, this is for your general knowledge, that while in 1 dimension and 2 dimension, as I mentioned, you are recurrent, you come back, what is the average n? Is infinity. So you come back in 1 dimension, but it will take you on average infinite amount of time, which means that Fn will decay like a power law in 1 and 2 dimension, in so slow power law. So you saw many examples of power laws in this beginning of this class, but most of them are introduced by hand. So the point is that this Fn decays like a very slow power law, such that the average in 1 dimension and 2 dimension come for a usual random walk is infinite. So while you come back, oh, okay, you are happy, but it might take you on average an infinite amount of time to come back. So you have to wait, and you understand why even in 1 dimension, let's say you have a random walk, you start here and you measure here. It could be that by chance your particle simply went in the wrong direction for a very long time, and then to return it will take a huge time, and then intuitively you might understand or expect that the average is not well defined because you don't have a scale here, a typical scale. Of course, this is a highly non-trivial result. I'm not saying that you should obviously see it, but you should understand the question. So the idea now was to relate between these two guys. These two guys are related, where the philosophy is I know this, and I want to calculate this. And how are they related? They are related by something called the renewal equation. So the renewal equation, let me write down the equation. So first of all, let us define the initial condition. So at time n equals 0, R0, this is the probability that the particle started at R0. What is the probability? Where is it in space? Well, at time 0, it's on R0. So this is simply a delta of Kronecker of R0. So the renewal equation is the following. P n R0 is equal to the sum of j equal 1 till n, P n minus j R. So this is where you want to reach eventually. P f j R0. I write it here as generality. Maybe later we can say, okay, in our system that I'm asking you to think, there's also translation invariance. So all the points are the same. So starting here and going there is the same as if you shift both the initial condition and R, it's the same thing. But so in that case, maybe we can call one of them the origin. But in general, this is more general. You can have biases, you can have different jumps. Maybe here the probabilities of jumping left, right, up, down are different than here, etc. This is a general equation, so I leave a general notation. But what, more importantly, what this equation says, it's really something very simple. It says the following. The probability that the particle is found at position R, starting at R0, when you have n steps, is the same as the probability that the particle starting on R0 arrived at R at some time j, j is less than n, and then here it arrived for the first time, and then after that it made a loop. There was a probability starting on R to come back to R in the remaining time, n minus j. So here you have n minus j, here you have j. The total time is n. Now, when did it arrive for the first time at this particle? This is this index j. It could happen after the first step, after the second step, any step, including the possibility that you arrived exactly on the last step, at last step n, and then this guy will be simply this delta function. Okay? So what it means is something simple, and that is, let us say we look at the paths. Here is R0, this is my path. Here, without the notion of first passage time, just probability n is fixed to something. And then I say, okay, it arrived my absorbing boundary condition, but then it continued because n is bigger than 1, 2, 3, 4, 5, 6, 7. And then it came back, and then it made another loop, went somewhere else, and came back. And then the probability of observing the particle at time n, so you see here the particle arrived for the first time, did a loop, then another loop, and you are here, and then this is your trajectory that will relate. So I'm saying here, this is the you see what is happening here. You have the probability to go for the first time here, and then the probability to make a loop. This is the loop from R to R. And this is the probability of the first part of the segment that depends on the initial condition. And all this is possible because each time I do a step in this random walk, the history is not important. So the fact that I arrived here after 20 steps doesn't influence the probabilities of transitions down here. That is what I called before the Markovian approximation, which is a fantastic approximation in random walk theory, and it's generically valid. So with this, you are essentially done in principle, but there are now technical issues, because I said before, this is what I know from somewhere, but I want to know this. Then, as I mentioned already in previous class, this is simply a convolution equation. Usually you are used to seeing convolutions with integrals. But you see here, if you look at the time, here I have n minus j and j. Here I have some. Usually maybe you are used to looking at convolutions with integrals, so that will be, for example, integration over time. So here I have a convolution, but which is discrete in time. Why is it so? It's very simple. It's because I assume that the random walk is discrete in time, right? I started with something, so I have no integration. And then we need to develop techniques which are similar to the Laplace method, Laplace transform method, to solve this equation, at least formally. And this is what we're going to do now. OK, so this was the general agenda. So you have any questions? Now we're going to solve this equation, first in generality, and then for specific random walks. So let us define now the discrete Laplace transform, also called the Z transform. So instead of n, I'm going to use now in transform space Z. And usually I had here a hat, but there's no need. If you have here Z, then you know that you are working in Z space. This is like Laplace. If I have here n, then you know that we are working in n space. So this PZR and R0, by definition, is the sum over n equals 0 till infinity. Zn, this is the definition, Pn R R0, and this I can write delta when n is equal to 0, then I have the initial condition either 1 or 0, this initial condition, plus sum from n equal 1 to infinity z to the n Pn R0. This again is called the Z transform. And it's like the Laplace transform. So the claim is that solving the problem in Z space is much easier than solving this in N space. In principle, you can also do that in N space. For example, if you know this list, then it's an iteration. Why? Let's say N is equal, let's say 2, then you relate it to F1. F1 you relate to N equal 1. So by iteration, you can solve these equations. And now we're going to solve them completely in Z space. Let us just, the Z space is like a transformation from like Fourier or Laplace, so sometimes it's not so useful. But for example, if I put here Z equal 1, then I get simply the summation over all the Pn's. So Z equal 1 is going to be important later. You will soon see why, and you will see it even better when you have Fz. So what is Fz? It's the same definition. It's the sum of n equal 1 till infinity, z to the power n, fn r0. Here there is a small issue. That is, let's say you started here and you also want to measure here. This is the return problem. So how do we at all define what is the first return problem? You don't define it on 0. You say n equal 1. The particle is here or here, let's say with probability half, 1 for each location. And then it can come back. So the first passage time is always bigger or equal 1. It can be 1, for example, if you start here and go here. But if you start and measure at the same point, the idea is first generate the step, and then you can come back. So n is always never 0, because it's stupid to think about it as n equals 0. It just means you started at the same place you measure. Of course, yeah, you can get this, but this is how we're going to define it. That's why here I start with n equal 1. Okay? So now the point is that where we want to relate this pz and this fz. So, for example, if I know this fz, I can do many tricks. For example, let's say I know this. I can relate it to this. So, for example, f of z equal 1, this is the sum over n, fn r0. But what is this? This is exactly the probability that eventually you will be detected. This is what I want to know. This is the probability to be eventually detected, or to eventually arrive. You can come after the first step, you can come after the second. The total probability is given by this, and this is what we want to know. We want to know if this is bigger or smaller than 1. So z equal 1 is important. And similarly, let's say you want to calculate the moment, the average n. What you need to do is you need to take a derivative with respect to z, and then you will have here an n. Then you take z equal 1, and then you will have here n fn. So this is like a moment generating function, this object. If you know this in z space, you know the average time. With simple derivatives and taking z equal 1, you can calculate the fluctuations. And of course, you can also calculate fn. So let's say I give you fz. How do you calculate fn? What do? You take the derivative of this fz with respect to z, let's say 1 time, and then take z to 0. So notice that fz r0 d over dz, and then z equals 0. So you see you have z to the power 1. This gives you f1 in, this is in real time, not in z space, in time, r0. So then if I want f2, I simply take the second derivative with respect to z. Then I need to divide by 2, and then I'll get f2, etc., etc. So derivatives with respect to z at z equals 0 give you the fn. That's one way to eventually, if you want to, extract back the information. So the values of the probability themselves are given by derivatives, while moments and total normalization are given simply by summation on z equal 1. So z equal 1 and z equal 0 are important for extracting data from this transformation. Of course, this is not new. It was the same with Laplace transform and Fourier transform with characteristic functions. But now it's slightly different because it's discrete, but it's kind of the same thing. So let us see what can we do now. So let us start with this equation. Let me copy it. So we have pz r0. This is equal to, here there is a mistake. Why didn't you tell me? Delta r r0 plus sum n equal 1 till infinity z to the n Pn RR0. And now you see here Pn RR0, I'm going to just put in the equation, the renewal equation, this is the renewal equation in time, and then we will see what is going to happen. Then this is equal delta RR0 plus sum n equal 1. And you see in this equation I have the summation over j. So this Pn will include the summation over j. So I'm using the renewal equation. So, and then I'm going to, okay, let me n equal 1 till infinity. Then I'm going to have the summation over j equal 1 till n. So let's say n is 20, then I sum up till 20. And then I'm going to write it like this. I'm going to write it like Zn minus j, Pn minus j RR. This is again the loop that you come back. And Fj RR0. And here I have z to the power j. So you see I add here z to the power n, and I did this very simple trick. I wrote it as z to the power n minus j and z to the power j. So the sum, I mean n minus j plus j, is simply zn. I hope everyone sees this. And the reason is pretty obvious. Now you see here that these two guys, here I have n minus j and minus j, here I have j and j. So this, I'll simply write down, this is RR0 plus, I'm just going to tell you what is equal, then I'll explain why. So here you can easily show, and wait 1 minute and you'll see this, that this is equal P ZRR times FZ RR0. And essentially we are done, because now we just need to, if I know the probabilities, I can just put them on the other side and then I can have Fz. Here you see that there is a special difference between something which is called the return problem. If I'm interested in Fz, the return problem is when R and R0 are the same. So when you start and measure at the same point, this guy is going to be 1. When you don't start at the same points, you're talking about a problem called the transition problem. You transit from here to here, and then this guy here is 0. Again, when you start and measure at the same point, it means first make a jump, then you might come back, and you want to know what is the first passage time distribution. So this is essentially the solution in Z space. It's very simple now because there's no convolution, it's a multiplication. So you add a convolution, and what happens with convolutions? You get multiplications as usual. Just let us see just remind me, it's kind of easy to prove why this is correct. One way is, let us look. So this you can do in homework, but let us look here what happens on this part of the equation here. Let's say j is equal 1. So what do we have when j is equal 1? We have sum of n equal 1 till infinity, z to the power n minus 1, p n minus 1 rr, plus, times z, this is this j here, z to the 1, f1 R0. Now what I can do is I can change indexes n-1 going to k. So this guy is equal zf1 R0 times sum over k from 0 now, because n equal 1, now you have k, till infinity, z to the power k, pk rr. But what is this guy? This is simply pz in z space, k is in time, this is in z space, rr, times z f1 going from r to r0. Now, if you do the same now for j equal 2, then you fix again. Now j is equal 2, but you need to sum over everything. But you should remember, of course, that if n is equal 1, then j cannot be 2, because the j is from 1 to 1 if j is equal 1. So n here is going to start from n is going to start from 2. So then in the similar way, you'll see that you'll get here zf2 z squared, because j is equal 2. And then when you will perform the rest of the summation, you'll get sum of n from 2 till infinity is z n minus 2, because j now is 2, p n minus 2 rr. And then you change again, you change n minus 2 is equal k, and you see here again this is equal z2 f2 rr0 pz rr. The point here is like this. The main message here is you see that now I add j equal 1, 2, etc., etc. You see here I get these guys multiplied by these guys, and then when I'll sum up more and more terms, I have z times f1, z2 times f2, but that is the definition of the generating function in f space, right? So that's why eventually you get this multiplication of f and z, just by going in higher and higher terms. This is only one way to show it, but again, this is simply the convolution theorem. It's the same as the proof of the convolution theorem. When you have integrals, it's something very similar. Okay, so we solved the problem, and now let us see some consequences of this. So, the first thing to do is solve the return problem. So the return problem is defined when the return problem is nice because you don't have an initial R0 and a place to absorb. R0 is equal R. So this is nice because you have one less parameter in the problem. It's related to the following question. You are here at the end of the class, or very soon you will leave this, and then you want to know, will you return back? So you don't, it's not like when, before you arrived this class for the first time, you came from somewhere else and came here. These are two different problems. So the return problem is, when you deal with these type of problems, you always start with the return problem, because you get rid of the initial condition. You get rid of R0. It's easier to analyze. And of course, these problems are not totally independent. When you talk about the transition problem, R0, then you're interested in questions like, let's change the distance between where you want to see the particle of the first particle R0 and see the dependence on the distance. So you lose something by taking R0 equal R, but that's the first thing to do just for simplicity, and also because it's by itself an important problem. So when you, let us say, we are going now to treat only the return problem. R equal R0. And then f of z, just using this equation, this is 1. I'm just going to move p of z I know in principle. Again, easier said than done. So when I take this guy, when I take this guy, this will be 1. And then I divide by pz, then this guy is, so here I have R0, R0. Because, again, initial condition and final position are the same. This is equal 1 divided by 1 over pz R0, R0. And I want to say something smart on this. So as I mentioned already before, let us look at the simplest thing. What happens at z equal 1? And as I already mentioned, this is simply the probability of return, no matter after how many steps, after n steps. This is simply sum over the fn's. This is equal to the sum z equal 1 to the power n, fn, obviously, because 1 to the power n is 1. So this is equal f z equal 1 R0, R0. Now, let us now also simplify and have in mind some translationally invariant system like a lattice. We're talking about a random walk on a lattice, that each point, this is translation invariance. So returning to this point is the same as returning to this point, or the same as all of them are the same. So I can call this point R0, one of them, but they're all the same. We can call R0, let's call it simply 0, just because it's nicer. This equation is general. You can have a lattice which is not translation invariant, and this will be valid, but let us now just simplify and assume that you have translation invariance, and then you have the following result: f z equal 1, 0, 0, coming back to some point on the lattice, is equal 1 minus p z equal 1, 0, 0 to the minus 1. All points are identical. I can call one of them 0, and that's it. Call it the origin. Now we can prove Polya at last. If you understand what is this object, P. So one way is, okay, like what I said before, let us do the Fourier transforms, but come on, it's not needed. You see, what is the probability that you will measure is eventually that this guy, if this guy is infinity, you have 1 over infinity, then this guy, it means that you measure with probability 1. So now we have to think why this should be infinity, or when is it infinity and when it's not. And the answer is, it depends on the dimension of the random walk. So what is P0 at 1? And this is very it's still very general. As I mentioned, this is the sum of a z to the n, Pn 0, 0. what is this? This is the probability. You started random walk somewhere, it does a random walk, it spreads out in space, then you go back to the origin, you ask what is the probability to be there? So this is equal to a sum, and let us write it in dimension 1. So dimension 1 is d equal 1, dimension 2, and dimension 3. You should know the answer. So what is it in dimension 1? And again, I'm not asking what is it exactly. I don't care about prefactors here. I care about, does this series converge, yes or no? So the sum is from 1. How can it be infinite? It can be infinite because of the behavior of this function at large n. This is what is important for us at this stage. Later on we can be more specific if we want to calculate exactly. So what happens in large n from the point of view of convergence? What happens in one dimension? What is Pn 0, 0 in one dimension? Who knows? In dimension 1. You have a random walk on a lattice. You start here. This is my 0. You start here at time 0, then you jump left and right. What happens to the probability on this point? It goes down because this guy is spreading more or less like a Gaussian. How does it go down? What? 1 square root of n. Yes, thank you very much. So this is in one dimension. And how does it go in two dimensions? It goes like 1 over n. It's dimension 2. There's some number here, but I don't care about this number because Polya is he just wants to know, does it return or does it not? And in dimension 3, it goes like 1 over n to the power 3 over 2. This is dimension 3. You know this from the solutions of the diffusion equation, or you should know it. What is the solution of the diffusion equation in one dimension? It's a Gaussian. The Gaussian is decaying like t to the minus half in one dimension. That is the same as this n to the half. How does the Gaussian decay in two dimensions? You just multiply Gaussian in x direction and y direction. So you get this guy squared. And in 3 dimensions, you have 3 Gaussians in x, y, and z. Then you have this. So this is kind of well known from the solution of the diffusion equation. Diffusion equations indeed are continuum time, but it's the same in discrete space. So this makes sense. And again, this is random walk, so it's not part of this class. If you saw it for the first time, you need to think about it, why you have half, 1, 3 halves. In dimension d, let's say dimension 22, you will have 22 over 2. And again, this is only when you have translation invariance and the jumps are uniform in all directions, so there are no biases, etc. So this is a random walk on a lattice. All points are the same. But now we see what is happening here is I have here in dimension 1 n to the minus half. What is the sum? This is up till infinity. Right? This is by definition of the generating function. It's up to you sum up to infinity. If you have n to the minus half, this sum doesn't converge because of the large n behavior. Right? This is infinity. The sum in 2 dimensions, it goes like n to the minus 1. This one, this is also infinity. But the sum that in the large n limit goes like n to the minus 3 over 2, this is a finite number. It's a finite number. So just by these general things, we already discovered something very deep, that we discovered the following. For a random walk on translation invariant system, for a random walk on translation invariant session and translation invariant system implies immediately that there are no boundaries, because if there are boundaries, they are not translation invariant. In dimension 1 and 2, the random walk is recurrent. Mathematically, it means, you see this guy is infinity. It means f of z equal 1, 0, 0 is 1 minus 1 over infinity. That is equal 1. That means you return the sum over all the fn's is equal 1. You return with probability 1. In dimension d greater or greater than 2, including 3, of course, the random walk is non-recurrent. It just means that fz, mathematically it means this is equal 1 minus 1 times some number, and c is not equal to infinity. These conclusions are very general. They are not limited to cubic lattices. They are general for any lattice which is translation invariant. We can calculate this c soon if we know these pn's, and that is what we are going to do. But the point, this is the point of Polya. Polya says there's some generality. What is the generality? It doesn't matter what is the lattice. What is important is the dimension. For this type of question, there are many questions. So some questions depend only on very general aspects. Like, will you return? This depends only if you are in dimension 1, 2, or higher. You can ask other questions, for example, what is this C? And this will depend on the lattice. It depends on the specifics of the problem. And we're going to calculate it now. But the main theorem is actually this. This is Polya. And you see, we didn't do anything specific. We just know something on the return to the origin, the Pn on the origin, how it decays in time, and then you know something on the first passage time. Okay, so now let us be more specific. From the point of view of the probability to return, it's now obvious that 1 dimension and 2 dimension are boring, because the answer is you return with probability 1. What you want to do now is to say something interesting, you need to work in dimension 3. I will skip 4 and higher dimensions. So the question now was translated from, I had it here, but the main point is we want to calculate, we need information on this probability, not on the first measure. The first thing is to calculate information on the Pn. If we know this, maybe we can do something and get something on the probability of detecting the particle eventually. And so this is the question, P n 0, 0, what is it? Again, I already described the general methods to do this, but we didn't do the details of some of the calculations, so now we are going a little back, maybe 2 or 3 weeks backwards. We're going to calculate it. And the main message from previous classes was that there is some characteristic function in Fourier space And this, once you know this, this defines the random walk on the microscopical scale, on the level of the simple jumps. Then you can know, in generality, you can know actually Pn k R0. Here it's translation invariant. R0 is, and this is the Fourier transform of the probability to be on R. From this Fourier transform, in principle, you can go to also the point 0 in space. But this message was, we talked about it many times in continuum problems and in discrete problems. Simply said, just let me remind you, for example, EI sum over XI. So this was the Fourier transform of the sum of many small jumps. This is simply equal to f of k to the power n. You remember this, I hope. N was the number of jumps, which now I use small n. And f of k was the Fourier transform of one individual jump. Right? You remember this. Now we are on discrete space, so it's a little bit different. It's a set of Fourier integrals. It's Fourier. We are working with Fourier series. But again, this is minor. Let us be slightly more specific. So, because we are dealing with lattices, right? So let us define. So what is f of, let's say, delta x in general is the probability, the PDF of making a jump of size delta x along the random walk. Each time you are at time n equal 22, you generate from this probability distribution, you generate the size of the next step. That's the microscopics of the random walk itself. So, which I want to relate to this Pn. So, what are we talking about? It's rather simple because we are limiting ourselves to lattices. So I have a lattice in one dimension, and then the simplest random walk is I'm either here, it doesn't matter where I am, I have a probability half to jump left or right. I toss a coin and either I jump left or I jump right. So what is f of x of delta x in this state? It's half times delta of delta x plus 1 plus delta function of delta x minus 1. Because this is the lattice spacing, I choose it to be, this distance I choose to be 1. If you're a pain, you can call it a. And then instead of 1 here, I'll have a. So 1 is the unit of the lattice. I just put it on the integers. I call this point 0, this point 1, this point 2, etc. And then you see here, I have a probability half that the size of the jump is minus 1, and the probability of the jump to have minus 1. That's a discrete random walk where you always jump a size which is order 1. Now I need to take the Fourier transform of this. The Fourier transform of this, I just multiply by e to the ik, and I integrate over delta x. So what do I get? I get here e plus ik, and e minus ik. So it's very easy. I hope you can see this. That f of k is simply cosine k. For example, if k is equal to 0, this is normalized. This is 1. Then if I expand it, then this gives you the probability, it gives you the variance. It's an even function. That's why the first term is 1 minus k squared, because there is no mean of the jump. The mean is 0 because probability half you jump left and right. So this is this cosine function. I think it was in the class already. This is the Fourier transform. Now, this really describes the microscopics, and the whole goal of this is to say, depending how you define the macroscopics of the jumps, of course, the final probability will be eventually defined. So now let us go one step forward. This was easy. This is in one dimension, but in two dimensions, it's as easy. So two dimension, and we have a lattice. And let's say you are here, and then you jump with probability quarter to nearest neighbors. In this case, f of k, here k was not even a vector because you're in one dimension. Here you'll have the following. You'll have 1 over 2 cosine kx plus cosine ky. So now it's slightly more complicated, but I think you'll understand. K is a vector, kx, ky, and the Fourier transform is a sum now of 4 delta functions, so that's why I don't write, because you can go up, down, left, and right, and these are in the y and the x directions, and then you get this result. For example, if I take both kx and ky to 0, then I have 1 plus 1, 1 over 2, that is the normalization, because f of k equals 0 has to be 1. That's the total probability to make a microscopical jump, etc., etc. And similarly, if you think about 6 delta functions in 3 dimensions, so in 3 dimensions you have, and then also something going out of the blackboard and something going in of the blackboard, and you are here, so you have 6 nearest neighbors, and then again, it's only for the cubic lattice now. So in 3 dimensions, you have f of k, the sum of 3 cosines, and this is 1 over 3 cosine kx. It's not k times x, it's k in direction x, because the lattice spacing is always 1, plus cosine ky, small y, plus cosine kz. And you can continue at home for 4 dimension. Now, what do I need? I don't need this f of k. I need the probability to be on n, to be on the origin after n steps. So just as a reminder, what is Pn R0? So this is equal to 2 pi to the power d. This is from the Fourier series analysis. Again, I already showed it to you, more or less. And then I have these inverse Fourier integrals. And I have d of them. So it's going to be interesting. They are, in dimension 3, there are 3 integrals. And then I have a f of k to the power n. Remember, this was the convolution. So the size of the jump I write it in dimension in Fourier space. I take to the power n, and then I do the inverse Fourier transform. And then here I have exponential. This is the inverse Fourier transform minus k r. And then I have integration over all the k's. The dimension in 3, integration in 3 dimensions, or 2, or whatever. Luckily for us, we don't need all this object. That's a good. It's not the continuous. You see, it's not from minus infinity to infinity. It's from minus pi to pi. This is the Fourier series. And remember that I showed it to you, if you remember. Even I don't remember, but I showed it to you in previous class, that when you do a binomial random walk, you have f of k was with its cosines, and then the coefficient, it was with bias, if you remember, with p and q, and then you have this cosine, and then you have this, so this is not continuous. This is discrete space and discrete time. This is discrete time, this is discrete space. Fourier series and not Fourier integrals. So luckily for us, we don't need here R. That's very good. We just need R equals 0 because, as I already mentioned, we need eventually PZ RR, which was 0, 0. So what I need here is Pn 0, 0, which is slightly simpler, 2 pi to the power d, integral from minus pi to pi, blah, 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 depending on dimension, f of k to the power n, k is a vector, ddk. But I don't really need this, right? What do I need? I need P not in n, not in time, but in z space. Because you see here, P in z space on these points, 0, 0, some point on the lattice. Because maybe you're already sleeping, I'll just write it down, 2 pi to the power d, minus pi till pi, minus pi to pi. Then what do I need to do? I need to multiply here by z to the n. This is just the definition of the z transform. You take the function, which is a function of time, n, and you multiply it by z to the n, and then you need to sum over all the n's. F of k to the power n, ddk, and here I have the sum over n, and if you remember, it's from 0. But this is an easy sum. You see, this is z f of k to the power n. This is just a geometric series. In all these businesses, you saw this before, you always have some geometric series, or many times you have a geometric series, and this I know how to sum. If you think about it a little bit, you can see it from here. This function f of k in absolute value is less than 1. So the series converges. And also what do I really care about is z going to 1. So this object, you can think about it less than 1. So the series converges when you sum till infinity, and it's given by a well-known expression. So essentially we are done. Not yet, but we are becoming close to the final point. So we have P0, 0 is this nasty integral, 2 pi to the power d, integral from minus pi to pi, minus pi to pi, 1 minus f of k, and f of k depends on the dimension and generally also on the lattice, times z, ddk. But actually, when you think about it, what do we really need? I don't need z in general. What do I need? Z equal 1. So again, this is for z equal 1 only. This was because now I just want to calculate will the particle return or not. So z equal 1, then I can delete this z here, and then I get this answer. So this is a function. And now we have the answer. We know, I called this number before something like C or something like that. So probability of returning in any dimension that starts from R 0 equals 0 going to R equals 0, 0 to 0. This is the, it's not the proof, it's the probability. This was 1 minus this object. This equation we had already, but now the new thing is this guy. Now we have it explicitly, right? explicitly as an integral. So, but for me this integral is, you plug it in Mathematica, you can solve this in principle. I don't know how, in general we cannot solve this integral exactly. Let's say in 3 dimensions, even for a cubic lattice, but I can take this thing, I can plug it in here and see the answer. And I'll soon give you the answer. But let us first walk in dimension equal 1. We know the answer already because we know, I hand-wavingly, I told you Pn goes like n to the minus half, the sum of this diverges, everything. Let's see it from here. So in dimension 1, what do I need to calculate? I need to calculate this Pz equal 1, 0, 0. And this is equal, dimension 1, you have here only a 2 pi. Integral from minus pi till pi. And in dimension 1, I just need to integrate over k, because there's only one coordinate. And here I need to write 1. This is this one. And here, what is this fk? This is simply the cosine. That's the, this is fk. Again, this is on a lattice, jumps to nearest neighbors, probability half, no bias. And you see that this integral diverges. I hope you see. Why does it diverge? From what behavior of k? This is from k close to 0, because when k is close to 0, 1 minus cosine k goes like 1 over k squared. Forget about the 2. The expansion of this is 1 minus k squared over 2, right? So you have here 2 when k goes to 0. So when you integrate this object, you need to integrate close to k. This is 1 over k squared. 1 over k squared, when you integrate close to 0, is 1 over k. At 0, this diverges. So you see here that this integral is infinity, and then this guy is infinity, and then the probability of return is 1, as we mentioned already. The difference is that now we look at it in k-space, and now we make it more rigorous, but we said it already. There it was for large n, now it's for small k. The divergence comes from small k. The same thing happens in dimension 2. Then you'll have an integration, which is twice, but similarly, for d equal 2, if you don't believe me, just take the expression I gave you for f of k and do this integral. Put it in Mathematica, it will tell you infinity. But for dimension 3, this doesn't happen. So in dimension 3, if you solve this integral numerically, so what is the integral? Let's write it explicitly. P z equal 1, 0, 0 is 2 pi to the power 3, integral from minus pi to pi, minus pi to pi, 3 times, because we are in dimension 3. d3k 1 minus 1 over 3 cosine kx plus cosine ky plus cosine kz this number is roughly 1.516. It's good that this number is bigger than 1, because you see I need to take this number and the return probability is 1 over this. So from here, the probability of return for a cubic lattice is roughly 0.34. Which means that if you start on a cubic lattice in dimension 3, you return roughly only 1/3 of the time, and the other 2/3 of the time you go to hell, you go to infinity, and you don't come back when you start, of course. So this is just shows you it's not close to 1, it's not close to 0, it's some number which depends on the structure. And if in principle, if you wanted to, you could calculate it for different lattices, and different lattices have different numbers, and your probability of return is not universal, the number itself. The question, will you return or not, that is universal, which means that in 3 dimensions with translation invariant lattices, you never return with probability 1. However, there is some probability to return, but that will depend on what is your lattice, what is the structure of the random walk, and on the details of the system. Okay, so what's the time now? Okay, so let us go for 15 minutes break. I'll have one more remark. So, and then we'll go to 15 minutes break, and then we will jump to a very different approach, which is in some sense more useful. We don't want to work all the time with discrete time and space. I'll briefly introduce you to the case where the time is continuous. But long time ago, people looked at a guy called Montrol. He considered the dimensions greater or equal to 3. And he was interested in the limit, d actually going to infinity, d large. And he showed that the return probability for cubic lattices can be expanded in the dimension. So this guy is equal to 1 over 2d. 1 plus, most likely I have a mistake here, but whatever, 2 over 2d, that's stupid. Ah, no, it's not totally stupid. 7 over 2d squared plus 215 2d to the power 4. You cannot solve it in generality. So you see these numbers are going down if the dimension is very big. And of course, the total probability of return is very small if the dimension is very high. Why am I mentioning it? I just like Montrol and I like this result. There's no special reason. So I'm just trying to say that there are many, many deep things going on. I didn't explain exactly how you calculate this series, but maybe saying the following, that even for cubic lattice, I don't think there is a result which is explicit for any dimension. I mean, but again, you can do this integral on a computer. This is not a problem. But if you want to see some picture, you need to expand in something big, and the something big is the dimension, and then you get these type of expansions to giving you a probability, just saying that the higher the dimension, the less likely you are to return, which is obvious. But some people made it specific by finding this type of series. Okay, so let's go for a 15 minutes break, and then we can continue with the first passage time problem a little bit more. Now we are going to treat a very well-known problem, and that is, we're not interested anymore in the question is, will the party come back, yes or no? We know that in dimension 1, without bias, the particle always comes back. Now we have to ask the question, what is the distribution of the times? So it will come back, then the question is when? And of course, because the paths are stochastic, there is a full distribution of this time, the time of the first passage. This is what we're going to study right now. But we'll take this opportunity to perform all the calculation in a very different way than what we did before. And this is a way that in many physics textbooks we use this approach. Instead of using directly the renewal equation, we use diffusion equation with some boundary condition. We need to understand this boundary condition, and with this boundary condition we solve the problem. So it's a very different method than previous class. You can do everything I'm doing here with what I did in previous class, on a lattice, all these things, but it will be much work, as you already saw. So we are going to do now a very simple way to solve the problem. So let us define the problem. What I consider now is Brownian motion in dimension 1. So it's not too difficult to do it. No, some part of the method is easy to generalize to dimension 2 or 3. Some other part of the problem is much more complicated. But we will consider this as the simplest thing. Of the simplest Brownian motion is in one dimension, of course. And the problem is the following. I start somewhere on the line. So this is space now. This is point x equals 0. And the starting point, I guess I want to start on the positive. Doesn't matter. And I want to start here at x equal a. So the way I think about this is going to be the time now. I have a Brownian motion. The Brownian motion is very similar to the random walk on a lattice, but the lattice spacing is so small you don't see it. So there is a continuum limit, which will be described by the diffusion equation. So you have a path, a Brownian path, and then this path goes, and then at some time you hit this boundary, and this time is the first passage time. So this guy is t first passage time. Of course, for different paths, so again, think about a lattice where this distance is much bigger than the lattice distance. A is very big. And then you can shrink the lattice to 0 if you want to be more mathematically. So some trajectories will go and you reach at this point, and other trajectories, you might go like that, and eventually you'll come back, etc. We know from Poynère's problem that eventually you'll come back, but you don't know what is the distribution of these times. So what we are going to calculate, or what we want to calculate, is the probability density of TF. And how will it look like, more or less? So this PDF versus TF, this is the random variable, the first time you hit this boundary. Well, at very short times, if this A is some distance away from the boundary, you cannot reach this place, right? I mean, you cannot reach it at the beginning, or so it has to be something like that. And then there is some time, and then you will decay. The area underneath this curve is, of course, unity. So the integral over the PDF, well, it's not so, of course, but now we know, dTF is equal 1. This is the from Poynère's problem. So you always come back, and the random variable TF can be anything between 0 and infinity. I mentioned already before that there is a very slow decay, and this is given, I'm telling you the answer, by this, it goes like TF to the minus 3 over 2. And you can think what are the prefactors here. The prefactors depend on the initial condition and one more parameter of this problem. The other parameter of the problem is the diffusion constant. The diffusion constant defines the diffusion. That's why it's called diffusion constant. How fast you move. If the diffusion constant is big, you expect it to arrive quicker than small, but maybe not, because maybe then it will take you to the other way too much. So we have here this random variable whose units are meters squared over second, and we have A whose units are meters, and of course time is defined by seconds. So already from here I can define a time unit, because d divided by a squared is 1 over time. That's a typical time scale of this problem. Still, so this might you might expect, but a again is the initial condition. A is not something universal. It's where you put the particle at the beginning. So this is one time scale of the problem. So you might expect that the average time is finite. The answer, no, it's not finite. It might be related to this time scale. Instead, you decay like this power law. And this means that the average time to return this is equal to infinity because of this t to the minus 3/2 times tf dtf. This is an integral over t to the minus half dtf for large tf, and this is equal infinity. So you return with probability 1, but the time it takes is infinity because you may go in the wrong direction because you have no bias. If you have a bias, then you will flow into this direction. If you have a bias to the other direction, you will not come back, etc. So there are many different rules. So we want to understand better how to treat these type of problems. The way to treat them is with respect to something called the survival probability. So we define a survival probability, which is a function of t or tf if you want. This is a probability of surviving. You are surviving in my class. Your probability of survival is pretty high. I admire that. And what is this probability of survival? You think about many particles that start here, and you ask, what is the probability that at some time t you are still in the domain? You didn't reach the boundary. Every particle that comes here is absorbed and removed. So this probability of surviving, what does it mean in surviving? In the interval from minus infinity to 0. Or you can switch it from 0 to infinity. From minus infinity to infinity, which means the probability of surviving is also equal to probability of not being absorbed. On x equals 0. And this is obviously related to the first passage time PDF. This is simply that the first passage time PDF is given by 1 minus integral from 0 to t, the PDF of tf dtf. So what is this guy? This is the probability that the first passage time was less than t. So this guy is the probability that tf is less than some t. T is a parameter, it can change. This is the integral. Then the survival probability is 1 minus this. This is the probability that you are absorbed before time t. 1 minus is the probability that you did not absorb. And what we are going to do is we're going to think, what is this? How we calculate this S of t, this survival probability. Because if we can calculate this, then of course the PDF of TF is simply minus ds. The minus is because of this minus dt, t equal TF. So we are done. In other words, calculating this survival probability is the same as calculating this PDF. And how does this survival probability behave? More or less, this survival probability as a function of time, it starts at 1, because you start with the particles here, right? So at the beginning, you are in this region, somewhere in this region. So you don't reach the boundary, so you survived. You were not absorbed. And at the beginning, it's going to be something like that, more or less 1, and then it will go down. And in one dimension, it goes down to 0. And the claim is that this guy goes down like t to the minus half. And this, if you take the derivative, you get this t to the minus 3/2. So now we want to think, how do we do this? How do we calculate the survival probability? Or first steps in the calculation of the survival probability. So Brownian motion, in general, forget about the boundary condition, is described by this diffusion equation, Px and t plus d, second derivative with respect to x, Px and t. This is the diffusion equation, and what is P of x of t? In general, that's simply the probability density function of finding the particle on x at time t. And in the absence, with free boundary conditions, when there's no absorption and no nothing, so for free boundary conditions, we already know if you start, let's say, on some origin, the solution is a Gaussian, and then as time goes by, the Gaussian is spreading, and this is because of diffusion. MSD, the mean square displacement, is simply 2 times d times t. We know everything about this equation when the boundary conditions are free. That means that we only imply that at x plus and minus and so forth, the probability density goes to 0. Of course, this is for a special initial condition, but this is the well-known solution. In our case, we don't have, it's not true that when you have absorption, when the particle, once it arrives at the boundary, is removed, you stop the process, and then it's not true anymore that we have free boundary conditions, we have an absorbing boundary condition. And with that, we will solve the problem and get the PDF. So it takes some time, or that's maybe the main point to think about. And the question is, in the presence of this absorbing boundary, well, I'm telling you the answer, in the presence of this, in the physical process, what is the boundary condition? And I claim the boundary condition is that P x at equal 0, so this is the boundary where the particles are removed, are equal 0. And this is called absorbing boundary condition. And the idea is rather simple. You have a path. It starts at A. Again, this is time t. And then once the particle arrives at this point, you actually remove it from the ensemble. It's not there anymore. You absorb it. So you demand this type of boundary condition, that the probability to find the particle here is 0 because you are removing it out of the system. Note that in quantum mechanics it's very different, and this is something to be confused with, because if you solve, for example, in quantum mechanics a particle in the box, this boundary condition conserves probability. If you remember particle in a box, you have a finite box, you have 0 and 0. But this is a different situation because we are dealing with diffusion equation and not with the Schrödinger equation. So this will cause the probability to remain somewhere else to be infinite. to decay in time. So what is the survival probability? The survival probability is the density from minus infinity to 0. This is 0.0, and this is minus infinity, px and t. At the beginning, this boundary condition doesn't play any role. You have some more or less Gaussian close to the initial condition, and then this is far away. The integral gives you 1. But as particles spread out, they fill the boundary condition. They are removed from the system. This boundary condition plays a role, and eventually this S of t decays in time. The one way to see this is the following. This guy decays in time. The particles let's put them somewhere. Let's say once they come out of here, they form a delta function here. So this is not, the particles are escaping this domain, but it's not that they are not existing. We don't kill particles. It's simply we're removing them from the system, and this is the total survival probability under this boundary condition that we are interested in the calculation of this guy. So then the question is, how do you solve this equation with this boundary condition? And that is pretty easy. All what I said is valid generally. I mean, in 2 dimensions, you'll have some boundary, which is, let's say, a circle or whatever shape you want, and you'll have this boundary in 3 dimensions, etc. You can generalize it. But now I'm going to use the fact that in 1 dimension, you can solve this very easily with a very well-known trick from electrostatics. And the method is called the method of images. So what am I actually solving? I'm solving the diffusion equation with this boundary condition. And the idea is I can do that schematically at some time t. I have a Gaussian solution. This is my absorbing boundary, and then I add here a mirror solution, which is the negative of the boundary. This point here is A. This point, or it's minus A, whatever. This point is A. So when I take 2 Gaussians, they evolve with time. I'll soon write it down. Both of these are both independently solutions of the diffusion equation, because you know this, because the Gaussian is a solution of the diffusion equation. One of them is negative, one of them is positive in such a, and they are centered on the initial condition in mirror fashion, such that here Px and T is equal to 0. So I add up these 2 solutions, and then I satisfy the boundary condition, and I satisfy the equation itself. The fact that you have here negative doesn't mean nothing. Well, what is important here is the probability here. And in this side, the probability will always be positive, because this solution decays, this also decays, but this point is closer to this source than this source. So here you always are positive, so everything is kosher from the point of view of positivity of the PDF. So the Px of t is simply equal to 2 pi dt square root. This is the famous normalization factor, if you want, of the Gaussian. And here I have x minus a. Actually, here I switch a and minus a, but it doesn't matter. Over here I have 2 dt minus exponential minus x plus a 2 dt. So to repeat what I just said, this is a solution of the diffusion equation. This is also a solution of the diffusion equation. So the sum of them is also a solution. But with this minus sign on x equals 0, you easily see here I have minus a squared, here I have plus a squared. They are the same, so they satisfy the boundary condition. Excuse me, px equals 0 for any time t. At time t equals 0, you have a delta function on A and a minus delta function on the source, like the image. But that is not in your domain. You don't care about it because it's outside your domain. It's here. Okay? So now all I need to do is calculate what is s of t, which is, as I mentioned already, the integral, let's say, from minus infinity to 0. Actually, I think here I messed up with the signs. This is with a minus, like that. Depends if you consider this a positive or negative, but never mind. Px of t dx. Now you have your integration over two Gaussians. It gives you something like an error function. Then after I take the derivative, this will be exercise at home. All this you'll have as an exercise later on. You get the following very well-known solution. The PDF of TF, the first passage time. Okay, you can start at A. This is my TF, this is my absorbing. So diffusion means there's no bias. Left, right is the same thing. This is equal to A 4 pi 4 pi dTF to the power 3/2 e to the minus a squared for dTF. And you see here a squared is distance squared, d is distance squared over time. So this a squared over d times t, the units are of course 1. And here I have a mistake. No, you see a and d, when you take, no, this is a mistake here. Yeah, sorry. Here 3. That's good that I checked the units. So you see d to the power half gives you distance, which will cancel this distance, and then you have t squared. No, over time, so you'll have time squared and half. This is correct units. So you see that the time scale is no, this is wrong. Come on, why are you sleeping? Here a squared. So you see here that the typical time scale enters. However, the PDF at large TF is simply given by a to the power 4 pi d to the power half to TF to the minus 3 over 2. And this 3 over 2 is what is important for us. That's the main issue. And as I said before, it means that the average TF is infinite. You always come back. How do I know that I always come back? The integral over this object is 1. So the time to come back, you always come back, but the time to come back, the average time to come back is infinite. Of course, the variance of coming back is also infinite, obviously, etc., etc. So there is no typical time scale, and this is because some of the trajectories, as I already mentioned, go the wrong direction, and then they will eventually come back, but it will take them a huge amount of times because there is no reflecting boundary, and this process is highly non-efficient search. So if you have a drunk random walker and he's coming back to his wife, which is she's waiting for here, many times it will take him to a long time to come back, very long time. This is, she will not wait, of course, but that's a different issue. So this is why this is called the drunken random walk. It's totally not efficient if the goal is to search. If you want to come from here to here, okay, you will find your target. If this is the initial condition and you are looking for something, the easiest search is a random walk. Why? Because then you don't need to build any machine on the guy who's doing the random walk. He's just the stupidest researcher, just jumping left and right randomly. So you are promised the searcher will find the target. However, it will take him on average infinite amount of time, which if the goal is to find something, this is very bad because you usually cannot wait so long for success. There is a famous and very helpful book only on first passage times, and this is called Guide to First Passage Times. So a book on this issue, and it's a nice book because it's not so big, it's quite short. This is the book that people take from my office and never give back. It means that many people like it. It's called Guide for First Passage Time. Maybe Problems by Sid Redner. And in that book, if you are interested, you can find many, many more examples, very simple examples with bias, higher dimensions, etc., where these type of problems are solved, and there are different methods of solution. It's a whole industry, a subfield in mathematics and physics. Okay, so what's the time now? Okay, so let me now briefly just tell you what we're going to discuss next lesson. So we're going to leave the issue of first passage times. And what we are going to discuss next lesson is going to be generally Brownian motion. Of course, we discussed this a little bit, but we are going to make it more physical. So up to now, we did the random walks. We had a little bit of physics, diffusion equations, but the theory of Brownian motion is much more physical than that. For example, when you have a real Brownian motion, which I mean by real is you have a system and you have a particle which, let's say, is 1 micron, and let's say it's in some fluid or liquid, let's say at room temperature T. Then there are many questions. So how did we define Brownian motion? We said there is some diffusion constant. How do you measure the diffusion constant? You measure the mean square displacement. You let these particles move in space. There's no bias, there's nothing. And then you measure, for example, the x squared in one dimension. X squared goes like 2 dt. After you measure this, you have d. And then you can make a prediction already, because then you can look at px of t. After you know this d, and you say, okay, this is a Gaussian, and this is independent of what is the temperature, what is the medium, what is the particle. It's always like that. And the shape of this PDF, this is what we know, will satisfy the diffusion equation. It will be Gaussian for free boundary condition. Now we know a little bit more. If you have some absorbing here, then you need to add the absorbing boundary condition, and you can solve it. But the very simple question is, what is D? So the first question is, what is D? The answer to this, what do I mean with what is D? What is D related to from physical point of view? So there are several answers, and there's no full answer. So the point is the work of Einstein. He didn't really say what is D for a given system. Why we cannot even do that in generality? It's super complicated because we have all the molecules interacting with this guy here. And when you change temperature, that's easy to check in experiment. When you change temperature, this diffusion constant changes. So there is no general theory what is D. But what Einstein said is that D is related to the viscosity of the liquid. So D is related to the viscosity. The viscosity is something macroscopical, not related to the small particle directly. The viscosity is simply given by the property of the liquid itself. You shear it, and then you can measure this viscosity, or you can drop a sphere in, you can measure the viscosity. So this was a property which was taken from hydrodynamics. Hydrodynamics is a well-established theory. In particular, there is the Stokes law. So we can relate this viscosity. If you know this viscosity, you know one more thing. You need to know the radius of the particle, you need to know the temperature, then you can relate between things. Of course, this is not a true microscopical solution, because then you can ask, what is this eta? This we not easy to find because of the complexity of the interactions, but we can relate between different measurements. So you can measure these macroscopical measurements of viscosity, and then you can get D. Or another thing would be to measure mobility, which is very common in condensed matter physics. And this is related to diffusivity. This is a second Einstein relation. And it says the following, this is the general framework. I can do several types of experiments on this Brownian particle. I can take this Brownian particle and let it move freely with no external forces. And then it will have some diffusion, and this is this diffusion. We understand this. Great. And now I can also apply a force. For example, I put here a charge on this Brownian particle, and then this particle moves in one direction. And how will it move? It will move with a constant speed. The force is acting on the particle, and you have a constant speed. Why is that? Usually you know that if you have a particle in free space, if you have a constant force, it will accelerate. But here you are in the liquid, so there's dissipation. So, of course, you know from your daily life that because of dissipation, of course, the velocity will eventually become constant. You know this very well because, you know, Aristotle told you that things reach some steady state because there is friction, and he was right and Newton was wrong in most experiences. So this is just because of the friction. You have this constant velocity, which is proportional. The bigger the force is, the more fast you move, but that's it. And this you well know. For example, you take a column of water, you have a bead, you drop it. It starts at velocity 0, the force is mg, and then after some time, the particle will reach a constant speed related to the viscosity because of the dissipation. So you can do this mobility experiment, again measuring with a force. But you see here Einstein saying diffusion is related to viscosity, but mobility is also related to dissipation. So all these things are related to one another. They all come together. And these lead to two Einstein relations, one between diffusion and dissipation, and one between mobility and diffusion. They are very much related. And this is what I call is a physical description of Brownian motion. So the big steps from physics point of view are not writing down the diffusion equation, because this is very similar to what mathematicians did, but rather relating between different observables that you do in different experiments and related between characteristics. So this is mobility is the theory of response of a system to electric field. This is all the conductivity, if you want, Ohm's law, whatever you want, all condensed matter. This is this. Diffusion is the fluctuation without a field. And this is, of course, the dissipation. So they are all actually related, and this actually brings a lot of beautiful things because, for example, when you hear a colloquium on condensed matter, they will many times discuss this mobility. But when they do calculations, they never calculate mobility, actually. Or most of the time, they don't calculate directly mobility. They actually calculate diffusivity. Why this guy is in principle easier than this guy? Well, they are the same, I say, but if you think about the physical problem, they are different. When you have a mobility, I said again, you have a force. So you need to add the force, and then you need to calculate everything. That's maybe difficult. You don't want to add the force, so what you do, you calculate the diffusivity, and then you know the mobility without, and in the diffusivity, the force is 0. So the external force is 0. Here the force is not 0. Now, it's true, so you can already hear, if you have intuition to physics, you say, diffusivity, when the force is 0, it's the fluctuations. Fluctuations of what? Fluctuations are characterized by mean square displacement, for example, and the mean from symmetry is 0. Mobility is actually defined by the average, which is proportional to velocity, some average velocity times time. Here, this is not equal to 0. This force is constant. Now, this is a great present that Einstein tells us, where he says, you know, for calculation or to think about it, you can think about diffusivity, and then you can get some information on mobility. It works, however, not in general. It works when the force is small. So this is sometimes also called linear response. It's pretty obvious that if I apply a tremendous force, let's say I put here a black hole and I screw up everything in this medium, then of course the force itself will influence the properties of the molecules themselves, and then you will not have this beautiful relation. So only when the force is relatively small, but most of the measurements, let's say Ohm's law, etc., they are relatively small, then you have a deep relation between mobility and diffusivity, or sometimes we call them also, they are also called fluctuation dissipation relations. What is the fluctuation? It's the fluctuation without the force. This is the MSD. What is the dissipation? It's the mobility or this diffusivity or this viscosity. All these ideas that started with Einstein in 1905 have been generalized in many ways, and we'll discuss some generalizations, because what Einstein was doing, and this will be discussed next lesson, he considered this diffusive process where you have this Markovian property. Each step is independent of the previous steps. In real life, this is an approximation, but it's not exact. So why not? So for example, when I look at this guy and I say, okay, I have diffusion equation. This describes the packet spreading of packet of particles. From physics points of view, there are many strange things here, and this describes very well a random walk and also many, many experiments. It's not that I'm against this. But on a conceptual level, there's something missing here. What is missing? Where is the velocity? So the Brownian particle is not described, or any object in classical physics is described, its phase space is described by position and velocity. In 3 dimensions, this is a 6 vector. During the random walk, we completely threw away the velocities. They just say probability to jump left, probability to jump right. But in real life, and in some experiments, you can follow the velocity of the particle. And the velocity of the particle is, in principle, an important ingredient of the dynamics. You cannot throw it away always. It really will depend on how frequently you look at the system. So in a real experiment, you actually sample, this is time t1, t2, you sample, let's say, positions or even velocities. If this is the sampling time. If the velocity has changed so many times in this small interval, then maybe the velocity is not important. But if you are able to measure quickly enough, you might see fluctuations in velocities and correlations of velocities. And this will depend on this viscosity. So it will depend on how fast you sample. So velocity is super important, of course, as everyone knows from mechanics. But it was wiped out under the rug when we treated the random walk. And now we're going to put it back into the theory and see how all this is related to one another. So this is done in the context of something called Langevin equations. And also Fokker-Planck equations. And these, if you want to read before next class, you should read slightly about them, about Einstein relations. This will be at the beginning of the next class. Okay, so thank you very much.